Hello everyone, this is Sir Aris. Today, let us discuss about Laplace transform. To begin, we'll have a few definitions. First, let us consider a review of the improper integral. An improper integral over an unbounded interval is defined as a limit of integrals over finite intervals. For example, if you have the integral a to infinity of ft dt, you can replace this infinity here by a. So you just take the limit as a approaches infinity. A is a positive real number if the integral from a to a exists for each a, and if the limit as a exists, then the improper integral is said to converge to that limiting value. Otherwise, the integral is said to diverge or fail to exist. Let us consider an example. Let f um, of t equal to ect for t greater or equal to 0, where c is a real non-zero constant. Find the integral from 0 to infinity of e ct dt. So from our definition of improper integral, we can set e ct dt as equal to the limit of 0 to say a of ECT, a limit of as a approaches infinity of integral from 0 to a ECT dt. Okay, that's equal to the limit as a approaches infinity of ECT over C integrated from 0 to a. So if we um, apply or we substitute the limits, we get the limit, or we substitute, we get the expression for this part. You have E C A minus set t to 0 is 1 divided by C. Or we take, let me just write it here, 1 over C, limit as A approaches infinity of E C A minus 1 over C. And as we can see, this function diverges for C greater than 0. So for C greater than 0, if A is infinity, then this is very large. So this is also infinite. So it diverges. For um, C less than 0, we get, actually, let me just write that here. For C greater or less than 0, C less than 0, ECA approaches 0 as A approaches infinity. So the integral converges for C less than 0. Third case, C equals 0, we get the integral becomes um, ECA CT from 0 to infinity. If this is C is 0, then you simply get 1 times dt, which is infinity. So it only converges for C less than 0. Another definition. Function f is said to be piecewise continuous on an interval if an interval t between alpha and beta, if the interval can be partitioned by a finite number of points, so that if f is continuous on each open subinterval, f approaches a finite limit as the endpoints of each subinterval are approached from within the subinterval. An example, you have this figure where the function ft is discontinuous. It changes. It experiences a jump as we go from, let's say, at point t1, then at point t2. It goes down to this curve. The integral of a piecewise continuous function on a finite interval is just the sum of the integrals on the subintervals. For example, for the function ft shown in the figure, we have the integral ft from alpha to beta is just the integral of ft from a to t1, from t1 to t2, and from t2 to beta. If f is a piecewise continuous function, then the integral exists. A useful theorem, if f is piecewise continuous for t greater than or equal to a, if you have this function f less than g and then m is less than t, if g integral on g converges, then ft also converges. If g diverges and if g is less than ft, then f also diverges. We will not prove this, but we will use it later. Okay, for the Laplace transform, or let's talk about integral transforms in general. An integral transform is a relation of the form. Here you have fs, integral of alpha beta to beta k st ft dt. Kt is a given function. It's called the kernel. Limits of integration alpha and beta. So what it does, you have a function f. So this is our function that we transform into fs. So f is called the transform of f using this integral and this function, the kernel function. We can transform f to fs. One example is the Laplace transform. If you have ft, uh, given for t greater than or equal to 0, suppose f satisfies certain conditions, then the Laplace transform of f, which we will denote by this calligraphic L, of f, a function f of t, or this is equal to fs, just like this equation, defined by integral from 0 to infinity of e minus st ft dt. And we need the improper integral to converge so that the Laplace transform exists. The kernel that we use for Laplace transform is e to the minus st. So the Laplace transform makes use of the kernel k equals e minus st. So the idea is you have to use Laplace transform to solve a differential equation. We transform some equation containing an unknown function f, and then that would give us some terms in the S domain, basically the transformed function f. We then solve this. It becomes an algebraic problem. We find f, and then after that we invert. So we recover the desired function f by inverting f. So we invert the transform. Um, To continue, let's consider first this theorem 6.1.2. Suppose that f is a piecewise continuous on a continuous function in the interval t from 0 to a for any positive a, and absolute value of ft is less than or equal to k. K here is a constant. E a t when t is greater or equal to m. So k, a, m are real constants. K and m should be positive. In this case, if these two hypotheses are satisfied, then the Laplace transform exists for s greater than a. To prove this, so what we need is to establish that this exists. So to establish the existence of fs, we split the integral into two parts. So our fs, which is by definition of the Laplace transform, it's minus st ft dt. We uh we, we use a point, or a point t equals m along the t axis. We call it m, e minus st ft dt, plus we start from m to infinity, e minus st ft dt. So this exists because that's our hypothesis here. Okay, piecewise from 0 to a is any positive, then this exists by hypothesis 1. Okay, here. Um, for this part, we use hypothesis 2. Using hypothesis 2, where f, absolute value of f, is less than or equal to k e a t. K is a constant. Okay, right here. Multiply both sides by e to the minus st. So e to the minus st of ft. Put it inside the absolute value. If k e minus st e a t. So this is equal to k e to the a minus s t. Now we use a theorem mentioned earlier using theorem 6.1.1. That's this. So you have two functions you're comparing. If this converges, then this should converge. Or on the other hand, if this, you have this two, if this diverges, then this should also diverge. Okay, so using theorem 6.1.1, since this here, or this is a constant, so we only consider this. So the integral m to infinity of e a minus s t, using the exercise or the example we had earlier, this diverges, converges for s greater than a. So the first example, in that example, we had c less than 0, which means that s should be greater than a. Then the integral of from m to infinity of minus this part here, st ft, converges. So we're comparing this and this, it converges. So fs exists. We have this two uh, converge, so fs also converges, then fs exists. Okay, so let's have examples. Find Laplace transform of ft, which is a constant, equal to 1. Okay, so our symbol for Laplace transform is cursive L or calligraphic L, and then we use braces. 1 is our function here. So Laplace transform of 1 is, by definition, it's 0 to infinity of e to the minus st dt. This is an improper integral, so we take the limit as a approaches infinity of 0 to a. e to the minus st dt. So we solve this integral that is simply negative e to the minus st divided by s. Evaluate from 0 to a. This is simply um, we set t to a and then t to 0. So we have this similar expression earlier, or so let me write as minus um, e to the minus sa minus, if we set t to 0, that's 1 divided by s. Okay, this exists, converges only. So for s, let's say, or for this exponent positive, if a is very large or infinity, approaching infinity, then this also approaches infinity. If it's 0, then the whole thing here, if s is 0, the whole thing is uh, infinite. If s is greater than 0, then the exponential of a positive number, if it's very large, approaches 0. So the Laplace transform of 1 is 1 over s, minus times minus here, for s greater than 0. Another example, find the Laplace transform of ft equals eat. Okay, taking the Laplace transform of eat, that's equal to integral from 0 to infinity of e minus st eat. This is simply integral from 0 to infinity of e to the minus s minus a t dt. Similar to what we have here, except that aside from s, we have minus, we have s minus a. And the answer is simply 1 over s minus a with the condition that s is greater than a. Third example, or for this section, the fourth example, find the Laplace transform of ft, ft being piecewise continuous. It's 1 for 0 to 1, 0 for t greater than 1, k at a discontinuous, at a discontinuity. But at a discontinuity, we don't really care about the value of f. So our Laplace transform of ft, which by definition is from 0 to infinity of e minus st ft. For this case, we simply have um, 0 to 1, because it's 0 for t greater than 1, e minus st dt. This is independent of k. The reason is because k is at the discontinuity. So we simply write this as negative e minus st over s, evaluated from 0 to 1, or um, this, if this is 1, this e minus s. If it's 0, that's like 1, but there's a negative sign here. Uh, so we can put down this 0 first to get rid of this negative. You have 1 minus e to the minus s divided by s. And our assumption, or our condition, that s is greater than 0. Okay, so for this to converge, s should be greater than 0. one more difficult example. Find the Laplace transform of sine AT. So the Laplace transform of sine AT is equal to Fs, which is given by 0 infinity of e minus st sine of AT dt for s greater than 0. Okay, this is, you have um, the limit as a approaches infinity of 0 to a from of e to the minus st sine AT dt. To solve this, we can use integration by parts. So using integration by parts, you have our Laplace transform Fs equals, so the limit as a approaches infinity of this integral. If you want to review integration by parts, we can set this equal to u. We can set this equal to dv. Integral of u dv equals uv minus v du. This is evaluated at the boundaries, so the limits of integration. Okay, so if this is 0 to a, this is 0 to a, 0 to a. Okay, so simply we have uv, so e minus st, and then dv is this. V should be cosine. Derivative of cosine is sine at times a, so there should be an a. Negative sign, I mean, so there should be a negative. Let's put the negative somewhere. Let's say I'll put the negative here. Okay, evaluated from 0 to a minus the integral of v is, again, that's negative cosine at. Let's put the a here. This is divided by a, and then du is derivative of this, so there's a negative, so the negative and negative uh, cancel, so this one has a negative supposedly, but the du has a negative also, and then there's an s, so let's put s and a outside, um, and then e minus st dt from 0 to a, taking the limits. You have if you set t equal to a and let set a approach infinity, the value of this goes from -1 to 1. So whatever the value, it will always be between -1 and 1. But this is if t approaches infinity, um, will have uh, or yeah, in the case where t approaches um, negative, or t approaches infinity, this term here would go to 0, this thing, so it becomes 1 over e to the st. T goes to infinity, so this is 0. This one is a finite number divided by a, so that's 0. Now if we set t to 0, this becomes 1, this becomes uh, 1 also. The negative cancels because this is the lower limit, so you have 1 over a. This is 1, this is 1. Negative cancels with the negative for the lower limit. And you have s over a from 0 to infinity of e minus st cosine at dt. This doesn't solve the problem yet. We apply a second integration by parts. So second integration by parts would give us 1 over a minus s over a, taking the limit as a approaches infinity of 0 to a e minus st cosine at dt. Oops. There's no need for this bracket. 1 over a minus s over a. You do the same method of integration by parts here. That would uh, give you, so take the limit as a approaches infinity of e to the minus st sine at over a. This becomes our dv. This is ru. Derivative of sine is positive, so that we don't need the negative sign here. We don't need this negative sign. And then minus s over a, 0 to a e to the minus st sine at dt. So we have here cosine at e to the minus st. Take the derivative of e to the minus st, you get a minus sign. Take the derivative of cosine, you get also a minus sign. But here, if we take the derivative of sine, that's positive cosine. So this is simply uh, positive due to the negative here. Okay, this is evaluated from 0 to a. This is again finite. If a reaches infinity, this whole term becomes 0. So you have um, 1 over a minus s over a. Uh, and then when t is 0, this whole term is 0. So we don't have any, so this limit doesn't have any, doesn't have any contribution to this whole term. So we are left with this. So you have s over a times s over a, that's s squared, a squared. A approaches infinity, so let's just set that to infinity dt. And again, it doesn't solve the problem yet. But this is now familiar. We simply went back to fs. Okay, so we have an expression fs equals 1 over a minus s squared over a squared times fs. And then we'll solve for fs. So this equation becomes fs plus s squared over a squared fs equals 1 over a. Okay, so you factor out fs, you have fs a squared, so you have a squared s squared equals 1 over a. So you have fs equals a divided by a squared plus s squared. Um, Suppose you have f1 and f2, two functions whose Laplace transforms exist for s greater than a1 and s greater than a2. Then for s greater than the maximum of a1 and a2, we can write the Laplace transform of c1 f1t plus c2 f2t equals integral from 0 to infinity of e to the minus st c1 f1t plus c2 f2t dt. Okay, so you have c1 0 to infinity e minus st f1t plus c2 integral 0 to infinity of e minus st f2t dt. Hence, we have the Laplace transform of c1 f1t plus C2 F2t equals C1 Laplace transform of F1 by definition. So this integral here plus C2 Laplace transform of F2. This implies oops, that the Laplace transform is a linear operator, which means that if you have a sum of functions, you can individually take the Laplace transform of one term, and then the Laplace transform of the sum is just the sum of the Laplace transform, just like for this example here. So the Laplace transform of the function is equal to 5 Laplace transform of e minus 2t minus 3 Laplace transform of sine 4t. What is the Laplace transform of e to the minus 2t? E minus 2t, let's go back to our examples that's similar to this. You have a, okay? Ax minus 2. So you have 5 times 1 over s plus 2 minus 3 sine of 40. So for sine, this is sine 40. Um, you have a is 4. Oh, hold on. Okay. So you have 3 times 4 over s squared plus 16. Okay. So this is for s. No, let me simplify this. So this is 5 over s plus 2 minus 12 over s squared plus 16. Okay. The condition for s is that s should be greater than 0.